Okay, we're going to continue on here. We're in chapter 8. So let us remember what was in chapter 8. I don't know. Let's see. We talked about some really important sort of conversions. Obviously, we talked about molar mass. And remember, molar mass we get from the periodic table. It has units of grams per mole. And it is the number that you see on the bottom. Typically, 4 significant figures is what we take. And then molar mass, remember, is really our conversion factor to go from grams to moles or moles back to grams. So if you ever have either of those two sort of conversions, it is the molar mass from the periodic table that's going to allow you to kind of do those conversions. And we can set it up with dimensional analysis like we talked about, grams over moles or moles over grams. And again, remember kind of doing things dimensional analysis kind of takes the math out of it a little bit. So just opposites is all you have to kind of remember. We also talked about Avogadro's number, which is 1 mole of anything is 6.022 times 10 to the 23. Remember the units here of Avogadro's number can be different. It could be atoms, it could be molecules, particles, it could be really anything. This is also a conversion factor typically that we use to go from moles to atoms or molecules are probably the two most common sort of conversions, and backwards. As we talked about last time, again, we do not want to use Avogadro's number unless we are given any number that's in atoms, any number that's in molecules, or you're asked to solve for one of those units. So again, if you're not asked to solve for any of those things, or you're not given a number that's in atoms or molecules, you really shouldn't use Avogadro's number. And probably the important thing that we talked about with that is this. Remember that again, this is the abbreviation for moles, not molecules. And again, that's again a super common error that people make. Um, and as I mentioned, pretty much in chemistry, if they want molecules, they will actually write out the word molecules. And that's definitely how you know they're talking about molecules in that case. We also talked about percent composition by mass, and percent composition by mass is basically you take the grams of the element you're interested in your formula, you divide it by the molar mass of the formula, and you times it by 100%. So, if we had H2O2, you would get the molar mass of this guy, and that would go on the bottom. And if you're interested in the hydrogen, you would go 2 times the 1.008 grams per mole up on top for the hydrogen, divided by the molar mass of H2O2, and you would times it by 100%. And obviously, you would continue that sort of pattern for each of them. Remember, it does need to add up usually to 100%. That way you got the entire compound that is present as well. We finished up talking about 2 types of formulas, which are our molecular formula and our empirical formula. And remember that the molecular formula is the formula that tells you pretty much exactly how many of each element you have present. While the empirical formula may not do that, the empirical formula is the simplest ratio of what elements are present. Now, it is possible, as we talked about, that both the molecular formula and the empirical formula are the same, but a lot of times you can reduce down. So again, C2H4 being again our molecular formula here, that again is a 2 to 4 relationship, which is the same as a 1 to 2 relationship, which means the empirical formula here would be CH2 in this case. Remember that these guys on the bottom are the moles, and they also do need to be whole numbers. So you can't have like a half of carbon or something like that. So it does need to be whole numbers. Those numbers that are on the bottom. So this would be a situation if you, for example, had the molecular formula and wanted to calculate the empirical formula, you could just reduce it down if it's possible. If not, then again, the molecular formula and the empirical formula would be the same in this particular case. Like we talked about water, I think, as an example, water is 2 hydrogens for every 1 oxygen. That's a 2 to 1 relationship, and there's no way to reduce that down any further and still have whole numbers. So it's both them. empirical and molecular formula. We also talked about the idea that ionic compounds, because we balance everything out to zero in the simplest way possible, when you see an ionic compound formula, it is an empirical formula because they have to be the simplest whole number ratio to get everybody to zero. We finished talking on how to actually calculate the empirical formula if you needed to do so. And remember, there's a few steps to do. First thing is really, for example, if you're given the percent composition, you can, as we talked about last time, kind of assume that you have 100 grams. And what that's going to do is essentially just turn the percentages into grams. It'll be the exact same number, just grams of each of those. Once you have everybody into grams, you want to then convert to moles. And again, that is what we use our molar mass to do our conversion factor, which is our grams per mole, which comes again from the periodic table. At this point, like we talked about, you will then have moles of everybody. You're going to divide by the smallest number of moles. So as we talked about last time, if you had, say, 4 moles of A and 8 moles of B, in this case, you would go through and divide everybody by the 4 moles, as that's the smallest. And that would give you a 2 here, and that would give you a 1 here. And if we do hit whole numbers, are really, really close to whole numbers, just maybe slightly over or just like slightly under, like 1.99 or something like that, like we talked about, that would give you your empirical formula. So that would be AB2 in this case. As we also talked about last time, sometimes when you do the division part here of the smallest number of moles, you do not get whole numbers. And in that case, if it is too far to round, you can't round. Typical endings, as we talked about, that are kind of too far to round, are like a 0.33. I think we did that one at the very end. We had one like that. A 0.50, also too far to round. So technically speaking, when you're doing this for the empirical format, it really needs to be almost like the whole number for you to round. Out a couple of decimal places, kind of, is where the difference lies and stuff like that. So if it is a situation like this, like we talked about, you do need to find a number to multiply the empirical formula by. So let's just say we had a B, I don't know, 1.5. In this case, if we took 1.5 basically times it by 2, we would get 3. We would then multiply not the empirical formula by 3, but by that factor of 2. And that would get us A to B, very badly drawn B there. B3 would be our empirical formula at that point. So you don't always hit whole numbers. A lot of times you do, but again, if it's too far to round, you do have to find that factor. Any questions on any of that stuff we were talking about last time? All right. So I don't think we did this one. So just to go through the steps with you one more time, I'll do this one, and then we'll kind of go through those processes. In this case, we're actually not given the percent composition by mass, but we're given the grams of each of the elements that are there. We're also given this number, and what sometimes happens is when people see multiple numbers, they feel like maybe they have to use them all. And in this particular case, you don't. The purpose of this number is that is the mass of the compound. And because of the conservation of mass, that basically means that the mass of the oxygen and the mass of the sulfur should actually equal that number. So if you took this number here and you added it to this number here, you should get this number. And what that basically tells you is you have 100% of the compound very present there, right? You know the grams of each of those. If you added those together and again it didn't add up to the total, then you're missing some type of element. And obviously, again, there would be some way for you to figure out what's missing, but that's the key. So in this case, this number here in the box is really just to make us feel confident that this is all the elements that are present at this point. They're already in grams, so remember, you never want to go backwards. So since it's already in grams, we could actually just move to the step of converting the grams to moles. And what we would need to do, once again, is go to the periodic table and look up sulfur, 3207, I think, right, if I'm not mistaken. Oxygen there is 16, I hope. And again, we're going to use that to convert our grams into moles. So we'll start with our sulfur. So we got 0.54 grams of sulfur. Remember what this means is there are 32.07 grams of sulfur in a mole. So the number always stays with the grams part. It's always per 1 mole. And as we talked about last time, it's essentially just going to be used as a conversion factor, really. So opposites cancel, which means I do need to put the grams on the bottom so that they cancel, and moles of sulfur up there on top. Dimensional analysis means multiply the top, divide the bottom. So in this case here, we're going to get 0.54 divided by 3207. Going to get us here 0.0168. I'm going to go 4. And again, I'm going to take it to a few digits so I don't round too much at this point. Again, so you don't maybe get rounding errors. And that will sometimes help you at the end when you're like, am I close enough to round or not round if you don't round too much here. We're going to go with 0.538 grams of oxygen. Once again, from the periodic table, that tells us the molar mass of oxygen is 16 grams per mole. Once again, opposite, so 16 is going to go on the bottom. Moles is going to go on top so that the grams cancel, and we will end up with 0.538 divided by 16. Going to get us here 0.03363 moles of oxygen. First off, any questions so far? Now that we got all the elements into moles, and by the way, just so we're clear as well, this is sometimes a common error that sometimes people make, especially when they see the word oxygen. So they think back to the diatomic molecule and they want to use like 32. But remember, you don't know how many oxygens you have, so you don't know it's O2, and it's probably not O2. So again, that is why we're using 16 in this case, because we don't know how many oxygens we have, right? So we're going to divide by the smallest, and to me, it looks like the top guy here is the smallest. So we're going to divide each of those by the moles that are the smallest in each one. That's going to give us a 1 there. And on this one, it's going to get us here a basically 1.9967. This is a situation that is close enough to round. So obviously that is pretty much 2 in this case. And since we essentially did hit whole numbers, that will give us our empirical form of SO2 in this case. Any questions on that there? So what I'm talking about, kind of close enough to round, it really should be fairly close to the whole number back here in that sort of area for it to be able to be rounded in most cases. Any questions on that there? All right. I did one, you do one. All right. So what is the empirical formula here of this guy? And carbon is 12.01 from the periodic table. Hydrogen 1. Take a quick look at them. And again, make sure that they are in the 100% ballpark. I would say most of the time you'll be okay, but there are some problems where it might not add up. So just make sure you're not missing anything. In this case, we're pretty close. I think we got 50 and about 50. So we are pretty good there. So because of that, we can then assume 100 grams. And again, the purpose of doing that is just to keep the numbers the same. So nothing is really changing here. So really all we have to do is just take out our percentage sign there and change it for grams. So we would then have 49.3 grams of carbon. We would have 6.9 grams of hydrogen and 43.8 grams of oxygen. And again, by assuming 100 keeps everybody the same numbers. The next thing we want to do now that we have the grams of everybody is convert everybody into moles. So once again, that is where the molar mass here is going to come into play for each of these elements. And again, from the periodic tables where we could get that. We definitely want grams on the bottom so that they cancel and we're left with moles. So carbon is 12.01 grams per mole. Hydrogen is, from the periodic table, 1.008 grams per mole. And oxygen is 16 grams per mole. Again, I'm going to put the grams of everybody on the bottom. That way, every gram there cancels basically. And we're going to be left with the moles of each of these. Yes? I'm gonna say yeah. Yeah. So just in general, like we talked about, besides the overwhelming fact that that is how they want you to show work as you go through all your chemistry classes here, it is, as we talked about, a really good way to do it because a lot of times you may not even have to remember like a formula or anything like that. If you just think about, okay, what units I want to get rid of and what units do I need, and opposites always cancel. So if you remember, dimensional analysis is always multiplying the top, dividing the bottom. It takes care of the whole rearranging and all that kind of stuff for you, and it just organizes everything sort of the right way. Yeah. Yeah. Other questions? All right, so go 49.3 divided by 12.01. Good catch. And again, as I mentioned, I personally don't like to round too much. You don't have to write every single number you see there, but definitely take it to a good amount of numbers there. And again, that will definitely help with any type of rounding sort of error or something like that along the way. So here we'll go 6.84524 moles of hydrogen. And lastly here, 43.8 divided by 16, 2.7375 moles of oxygen. Now we're at the point where we want to divide everybody by the smallest number of moles, and that does appear to be the oxygen in this case. So we're going to divide everybody by that oxygen number of moles, and hopefully we'll hit some whole numbers. We'll see here in a second. 375 here. So that equals 1. We'll end up with 4.10491 divided by 2.7375. Here we're going to end up with 1.5 basically. And 6.84524 divided by 2.7375 and a 2.5 in this case. So in this case, if we were to sort of write our empirical formula at this point, we got C 1.5, we got H 2.5, and we got O. And clearly, hopefully you could recognize these are a little problematic. They're also too far to multiply or to round. So here we do need to find a common number. You could probably just see it, but again, if you took 1.5 basically times 1, you got 1.5. 1.5 times 2 is going to give us our 3. And since that also is a 0.5, that 2 is going to work for that guy as well. That's going to give us a 5 in that case. So we do want to multiply the empirical formula by this factor of 2 to get everybody to whole numbers. So that should then, we're basically going to take this guy and times it by 2. And that's going to give us C3H5O2. And this would be our empirical formula at this point. I think I might have mentioned this last time. As you can see here, if you do come across a situation like this, where you have multiple sort of ones that you can't really round, you usually can find one number that will fix everybody by multiplying them across there. Yeah. Any questions on that there? Yeah. Say again? So the way that you calculate the empirical formula is after you convert everybody into moles, whichever one is the smallest, that's who you divide by. So it's always the smallest number of moles you want to divide by. Other questions? All right. Questions on calculating empirical formulas. So just like we could calculate empirical formulas, we could also calculate molecular formulas. And there's really 3 things that you need typically to calculate a molecular formula. And those 3 things are pretty much what we see here. You actually need the empirical formula. So either the problem will give you the empirical formula, or you need to go through the steps we just did and calculate the empirical formula yourself. So either it's given or you need to calculate the empirical formula. Once you have the empirical formula, you need to figure out the empirical formula's molar mass. And actually, that's we need to determine the empirical formula. I'll erase that. There we go. And the third thing that you need is the approximate molar mass of the compound. And the good news about that one is going to be given to you in the problem. So it will usually be given to you in a problem. It will say somewhere in the problem like the molar mass of this compound is approximately, and they'll give you a number, grams per mole or something like that. They may also, by the way, give you a range, like the molar mass is somewhere between like 50 and 70 grams per mole. So they may give you a range, they may give you an exact number, but typically speaking, the molar mass of the compound will be given to you. So the two things that you really need at that point is the molar mass of the compound that was given to you, the molar mass of the empirical formula that you probably calculated, and what that's going to give you is a number when you divide those two. And that number is what you're going to multiply the empirical formula by to get to the molecular formula. So for example, if I did this and it came out as a 4, and let's just say that this was my empirical formula here, and I did the molar mass and I got a 4, I would take my empirical formula and multiply everybody by 4, and it would give me C4H8 as my molecular formula. And that is what that number is for. Now, I personally am a fan of doing that version of it. I will say books, and sometimes people will do this and go empirical formula in parentheses and that little number on the bottom, and sometimes they'll do that. I personally think you probably should just multiply it out and just get the molecular formula like you might expect it to be, but you will sometimes see people kind of do it in these type of problems or give the answer that way, but I would recommend just multiplying it out to get to the molecular formula. Now, we talked about with the empirical formula when we're dividing by the smallest that we really don't want to round until we get are really, really close to the whole number. The one place where you could be a little bit more non-strict about your rounding is when you do this calculation here. And if it's close to the whole number, even if it's not really close to the whole number, you could kind of round to the whole number, because that number that you get when you do that division is based on the ratio of the empirical formula to the molecular formula, and it really should be a whole number. But the problem is sometimes you're not given the exact molar mass of the compound, so you're given an approximate value. So when you do this division here, you sometimes may not get a nice pretty whole number, so you can pretty liberally sort of round at that point to the nearest whole number. But definitely on the previous step when you did the empirical formula, you shouldn't be rounding unless it's really close. But here you could be a little bit more relaxed in terms of, okay, it's like you get like 1.3 or something like that. That's close to 1. You could call it 1 if you want. And again, that's because sometimes you're not given the exact molar mass, but an approximate value or even a range. So you may not get a nice pretty whole number when you kind of do that one. Any questions on that? Yeah. 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 So for example, either the empirical form will be given to you or you have to do the calculation. And let's just say hypothetically, this guy here was the empirical formula you got when you calculated, okay? So that is one of the things that you need to get to the molecular formula. I'll spit that out, I think. You would then need to take the empirical form and actually calculate the molar mass of it. So in this case, what we would do is we go 12.01, right, for the carbon, and we would add 2 times 1.008 for our hydrogens there. So you get approximately 14 grams or so per mole. You could do the real calculation there, but that would be the molar mass of the empirical formula, which is what you need. And that is what will go on the bottom of this division here. Now the top one would be given to you. So maybe in the problem they go, hey, the molar mass of this compound is about like 28 grams per mole, right? So you would then take the 28 grams per mole, which was the molar mass they gave you, and you would take 28 and you would divide it by 14, and you would get a number of 2 in this case, right? And that 2 is the factor by which you should multiply the empirical formula by, and it would tell you that the molecular formula in this case would be C2H4, and that's what you want to do there. So sometimes empirical form is given to you. I would say in most cases it's probably not going to be. You're going to have to probably roll through the empirical formula calculation first, then get the molar mass of that empirical formula, And the one thing that's typically always given to you in these type of problems is the molar mass of the compound. Somewhere in that problem, it will tell you that number and stuff like that. When we would do this, like maybe we'll do it in math, but yeah, so that would be an example. So yeah, so typically speaking, you would you would most likely in the lab, like you would do, or we'll do tomorrow, you would hit the empirical formula first because, uh, for example, you're going to start, for example, with like magnesium tomorrow, and you're going to do a reaction where it's going to basically add on oxygen to it to make magnesium oxide, right? Magnesium and oxygen together. So what you know and how the way you could kind of do this is you'll know the grams of magnesium you started with because you can simply go weigh it, right? And when this reaction is over, the only thing that you put on there is going to be oxygen. So this would represent at the end of the reaction the magnesium, the oxygen that you act the mass of it. And if you subtract the two, that will give you the grams of the oxygen, right? So you'll know the grams of the oxygen at the end of the experiment by just simply just subtracting the two masses. You'll know the grams of the magnesium at the beginning for just measuring the mass of the magnesium. At that point, you actually could just start rolling with your empirical formula calculation where you would convert those grams into moles, you divide by the smallest, and now you'll be able to figure out your empirical formula at that point. In terms of figuring out like the molecular formula, a lot of times they will do something like some more analysis of the compound and get an idea around of what the mass of it is, the actual compound, and then you could kind of get the approximate molar mass of the compound. You could experimentally, for example, figure out your molar mass of your empirical formula, and you could figure out, just like we kind of did here, a calculation of, okay, I know this is the empirical formula. The more mass of the actual compound is about, 4 times the mass. So you could multiply by 4 and you could get your actual formula of it. That 4 we compared to people and how people. The 4 is basically the ratio of the mass of the empirical formula, the simplest ratio of those elements that come together, to the mass of the actual compound of how many of each of those that are there. So it's, 4, say, basically what this would be telling you is the mass of the actual compound, the molecular formula guy, the actual compound is about fourfold the mass, fourfold as much massive as the empirical formula. And the only way you could do that is obviously it's based on the ratio of the elements that are present. All right, so let's take a look at this here. Why don't you give it a try here? What is the molecular formula of this compound that has an empirical formula of CH2O and an approximate molar mass of 60? So again, carbon 12.01. Hydrogen 1.0. In the cases that's not the case, you'll have to actually do the calculation. So since we have that, we can actually have the first thing that we need, which is the empirical formula. The next thing that we need is the molar mass of the empirical formula. So we'll just calculate that. There's 1 carbon at 12.01 in our empirical formula. There are 2 hydrogens at 1.008 from the periodic table. And there are 1 oxygen there. And that's going to give us a molar mass of that empirical formula of about 30.03 grams per mole. And again, that is our empirical formula that was given to us. The last thing that we need to figure out our molecular formula is what is typically given to you in the problem, which is right here. It tells us that the approximate molar mass of this compound is about 60. So the actual compound has a molar mass of about 60 grams per mole. And to figure out our factor that we need, we're going to take the 60 grams per mole, which is the molar mass of the compound. We're going to divide it by the molar mass of the empirical formula. So basically, molar mass of the molecular formula divided by the molar mass of the empirical formula, essentially. And if you do that there, obviously, as you might be able to see, you're probably going to hit something like a 1.998, which obviously is very close to a factor of 2. So what this is telling us is basically our molecular formula is twice as massive as the empirical formula. So that is the factor by which we're going to multiply our empirical formula by to get to our molecular formula. So it would be C2H4O2, and that would be our molecular formula in this case. Any question on that there? Yeah. Yeah. Yeah, so you could do one of two things if you're given something like whatever I said there, like say 50 to like 70, right? So you could either you could do the low end if you want, you could do the high end, or you could do what you said there, to go the middle route if you want. They will all give you approximately the same number. You will get a little bit further away as you get to the extremes, obviously. So if you can, probably the guy in the middle is probably the better choice. It'll probably put you closer to a whole number, but they all should kind of give you approximately the same number. Yeah. But you could actually choose any number in between that range, and it should kind of work. Yeah. Other questions? All right, let's try another one here. A compound has a composition of 1.52 grams of nitrogen, 3.47 grams of oxygen. Here's one with a range. It has a molar mass between 90 and 95 grams per mole, basically. Determine the molecular formula and the molar mass of it to 4 significant figures. So nitrogen here is 1401. And we got their oxygen, 16. Yeah. All right, so give it a go. Here, you're not given the empirical formula, so that's probably a good place to start, yeah? And kind of work through the steps there. One, obviously in this case, we're not given the empirical formula, so we do need to just go through the basic empirical formula steps. As we know, we need that to figure out our molecular formula. In this case, as I mentioned, they actually gave us a range of the molar mass of the molecular formula. So we could use any number really in that range. And again, that's one of the things that we do need. So the first thing we're going to do is just basic empirical formula calculation. So we're going to take our 1.52 grams of nitrogen. We're going to go to the periodic table, take that molar mass and divide it basically. We'll do the same thing for our oxygen, 3.47 grams of oxygen. You can divide by the molar mass there of oxygen from the periodic table. And at this point here, we will have 1.52 divided by 1401. That is not right. Try it again here. Punch it in correctly. There we go. All right, that is a 0.10849 moles of nitrogen. We'll do the same thing there for our oxygen, 3.47 divided by 16, 0.216, I'll call it 88 moles of oxygen. At this point, once you get everybody into moles, as we talked about, we're going to divide always by the smallest. And in this case, it looks like it is nitrogen is the smallest. So we'll divide everybody by the moles of nitrogen in this case. That's going to give me a 1, and I believe that should give me a 2, if I'm not mistaken. We will end up with basically 1.9999, which again is close enough, obviously, to 2. We hit whole numbers, which means our empirical formula in this case is NO2, and that is really the second thing we kind of need. We then need to go and calculate now the molar mass of our empirical formula, and that again, going back to the periodic table, 1 nitrogen of 1401 plus 2 times 16 for our 2 oxygens. That's going to get us basically 32 plus 1401, 4601. This is our molar mass basically of our empirical formula, which is basically the second thing that we need, along with our range of molar mass there for our molecular formula. Those are again the 3 things that we really need to calculate our molecular formula. Again, you could go 90, you could go 95, you could really go any number in between. You could go halfway there. So if you want to go like 92 and a half, which is somewhere in between those two numbers for our molecular formula, and divide it by 4601, that will give us our factor that we're looking for here, which is 2.01 essentially, which is basically 2. If you went the low end, just to show you, right, if you took the 90 grams per mole and divided it by the 4601, you will end up with 1.96, which is approximately 2 as well. And if you took the high end here and took the 95 grams per mole and divided it by the 4601, on the high end there, you will end up with 2.06, which again is also about 2. So really, any number that you choose is good. I personally think if you just kind of go halfway between the ranges, probably give you the closest to the whole number in most cases. So our factor is 2, and that is again what we want to multiply our empirical formula by. So we're going to take our empirical formula now, basically, and multiply it by 2. The subscripts on the bottom now give us N2O4 as our molecular formula in this case, yeah? Any questions on any of that there? Okay. All right, let's take a look at one last one, I think, here. Good look. Let's look at it a little bit longer. What is the molecular formula of this? Oh, by the way, obviously, I missed the last part of that question, which was what is the molar mass of the actual compound? So now that we actually have the formula here, we could calculate the actual molar mass of this guy. That would be 2 times 1401 for the nitrogen plus 4 times 16 for the oxygen. That would give us an actual molar mass here of 92.02 grams per mole, which, as you can see, was pretty close to the middle range of that, right? So it's kind of that ballpark. We could actually calculate it. And again, that's calculated obviously as 2 times 1401 for the nitrogens plus 4 times 16 for the oxygens there. Yeah. And that gives us the molar mass of the actual compound. All right. I want to make sure you answer all the parts of the question. That's probably a good idea. All right. Now let's take a look at this one here. We have phosphorus at 43.64%, oxygen at 56.36%. It's experimentally determined the molar mass is about 283.89 grams per mole. What is the empirical and molecular formula here? Phosphorus on the periodic table, 3097. And oxygen still 16 in all these examples. All right, so we're looking for two things, both the empirical and molecular formula. Let's see what you come up with here. Okay, let's take a look, see how you're doing. So once again, here we're looking for both the empirical and molecular formula. So obviously, we could calculate the empirical formula first. We are, in this case, given the percent compositions by mass. So again, looking at those percentages, it does add up to about 100%. So we're good to go there. That means, again, like we've done before, we could just assume that we have 100 grams of everybody. And that's going to keep everybody's number the same. So that will turn that into 43.64 grams of phosphorus. It'll also turn it into 56.36 grams of oxygen. At this point, we now are going to convert to moles. So using the periodic table there, we got our 3097 grams per mole of phosphorus. And for our oxygen, we have our 16 grams per mole. That's going to give us the moles of each of these guys here as 4364 divided by 3097, like a 1.4091, we'll call it, moles of phosphorus. 56.36 divided by 16, a 3.5225 moles of oxygen. Again, at this point, we are going to divide by the smallest, so that is phosphorus in this case, 1.4091. We're going to divide them both by. That obviously is going to give us 1 here, and when we do the second one there by the 1.409, that's essentially going to give us about a 2.5 in this case. That would give us an empirical formula PO 2.5. As we know, that is not so great. So as you could probably imagine, right, we can multiply by a factor of 2 in this case, and that would turn that into a 5. So remember, sometimes people multiply by the 5, but we actually want to multiply by the factor of 2, right? So we do want to multiply by 2 here, and that will give us P2O5, and that would be our empirical formula at this point. Any questions on any of those steps there? So we got one of the things that we need to get to the molecular formula. Now, while we have it, we might as well just get the molar mass of it. So to get the molar mass of our empirical formula, 2 times 3097 grams per mole for the phosphorus, plus 5 times 16 for our oxygens. And that's going to give us a molar mass of our empirical formula of, looks like about 141.94 grams per mole. That's the second thing that we need. And the third thing there is our molar mass that was given to us of the compound in the formula, or in the problem. We're going to take, again, our larger number, which should be our molar mass of our compound. 141.94 grams per mole. That's going to give us a 2, I believe, in this case. By the way, it will not always be a 2, but happens to be here. It does end up being a 2. We're going to multiply now our empirical formula by that 2. It's going to give us a P4O10 as our molecular formula in this case. So in most cases, this number on top should be larger, but it could also be the same as the number on the bottom, right? If the empirical formula and molecular formula are the same. So don't get freaked out. If you come across a problem like that, it can actually happen. Top number, bottom number are actually the same because both the molecular formula and empirical formula are the same. Yeah. It was actually given to us in the problem. And typically that number is usually given to you in the problem. Somewhere in the problem, they will give you kind of the molar mass of the compound, especially if they want you to do the molecular formula. So yeah, it's okay. Other questions? Yeah. Yep. Now, this is definitely a pretty safe approach to do it. I'm going to show you one more approach to this problem that you could take if you are given the percent compositions by mass, and you might like that approach better. But you really should only use kind of like what I'm going to show you if you do have the percent composition by mass, because you'll have everything that you kind of need to do that. Yes, sir. And no, but there might be a time where you add up the percentages and it doesn't equal 100%. And it may give you some other piece of information that will allow you to kind of figure it out. So for example, let's just say, it said, hey, this was 50% carbon. This was like 30% hydrogen. And maybe that's all they give you, right? And they're like, hey, what is the molecular formula or even the empirical formula? It doesn't really matter which one you want to do, or both. But somewhere maybe at the beginning, they say something like, hey, this is a compound that's composed of carbon, hydrogen, and oxygen, right? And they give you that kind of piece of, you would need some type of information like that. At this point, what we would know is, right, it's definitely 50% carbon, right? And it's 30% hydrogen, which if you add up those percentages is 80%, right? That would mean that although it wasn't directly given to you, the amount of oxygen there would be 20%, yeah? And you could get that by just taking 100% minus that, right? And that will get you the missing one. So sometimes you are given something like that. In addition, sort of variation of that is, you remember the problem we did at the very beginning there with the sulfur and the oxygen, where it said the compound had a mass of like 1.0054 grams or something like that. You may be given a mass like that and then given like the mass of a couple of elements, but they would also, again, kind of tell you something like that. And then you could just subtract the masses from each other and figure out the missing mass, and that will get you the missing mass. So that's probably more so what you would come across rather than that, yeah. Because if you are calculating the molecular formula or the empirical formula, You have to have everybody involved, right? So you can't not have 100% of the compound there, basically. Yeah. Other questions on that? All right, so back to this one here where maybe we want to take a different approach. So the approach that you could take is, I'll erase everything. So if you do have the percent composition by mass, right? We basically know that the entire compound basically has this molar mass. So you could take the percentage, for example, of phosphorus, and you could turn that into a decimal, as we talked about, right? Which is divided by 100 or move the decimal point. And you could take 0.4364, and you could times that by 283.89 grams, basically. And you can do the same thing for your oxygen, 56.36% oxygen. Turn it into a decimal, 0.5636, times it by 283.89 grams. And if you do that, that will tell you 0.4364 times 283.89. At a 283.89 molar mass, 123.889 of it is basically phosphorus. And if you do that, 0.5636 times 283.89, about 160 grams of it is oxygen. Now you actually have the grams of phosphorus and the grams of oxygen in the molecular formula. You can then divide these guys by the molar mass from the periodic table for each of those elements. So that was 3097 grams per mole. And divide this guy by 16 grams per mole. And if you do that, I ran out of room, so I'll come down this way. If you do that there, we'll take our 123.889 and divide it by 3097. You end up with a 4. And if you take the 160 divided by 16, you end up with a 10. And those are our molecular formula right there, yeah? So that was O10. That would then give you directly the molecular formula. So you can actually start with the molecular formula. Now that I have the molecular formula, how do I get the empirical formula? It is the simplest ratio, right? This is a 4 to 10 ratio, which is the same as dividing everybody by 2 here, a 2 to 5 ratio if you divided it by 2, and still get whole numbers. And that would then get you to your empirical formula. So if you have the percent composition by mass and you have the molar mass of the compound, you could multiply the molar mass of the compound by the percentage of each of those elements, and then divide those grams of each of those elements by the molar mass of those elements, and that will get you the moles in your molecular formula. And then at that point, all you have to do is reduce it down by simplest whole number to your empirical formula. So you can kind of go that approach if you like. Like I said before, I would probably only use this approach if you did have the percent composition by mass. If you just had grams, you got to waste your time to figure out the percent composition. You might as well just go through and do the empirical formula first and then go to the molecular formula. Yeah. Yeah, if you're comfortable with the editor method, just roll with it. Yeah, so this is just an alternative approach. As you can see, it can go a little quicker maybe than the other one, but the other one works perfectly fine. But if you're happy with the other one, I would recommend just rolling with the other one. But again, you may see somebody or somewhere along the way, somebody do it this way, and that is a way you could do it if you do have the percent composition. But you absolutely don't need to do it this way. If you like the other way, obviously you can see you get the same answers, right? This way just kind of takes you to the molecular formula first, and then you go to the empirical formula. The other way is you're starting with the empirical formula, going to molecular formula, which is perfectly fine. Which is more of the traditional approach, the empirical to the molecular formula. It's really good. Any questions on how to calculate any of those things? Yeah. All right, that is chapter 8. Yeah, that is what that says. All right, so we're done with chapter 8. We are going to then roll backwards, actually. We're going to go to chapter 6 now. Chapter 6 is a super small chapter. It's all about chemical equations, basically, and balancing chemical equations. So let's talk a little bit about chemical reactions. How How do we know a chemical reaction occurred? We talked a little bit about some of these things when we talked about sort of physical changes and chemical changes. Obviously, as we talked about, a chemical reaction is a chemical change. And as we talked about previously, what that means is what you start with and what you end with are fundamentally different things, right? Something has basically been made that wasn't there originally. You can't get back, right, the original part of it by any type of physical means, right? So sometimes that involves a color change. Oftentimes that's a solid that forms. That is sometimes referred to as a PPT or a precipitate. A bubbles form. Bubbles usually means that you made some type of gas, is usually the result of why bubbles form. Now, although sometimes the sign of a chemical change is not visual, heat or a flame would be visible, I imagine, but heat is either produced or absorbed. That is like an exothermic or endothermic type reaction. Again, you may not visually see it, but if you were, like, for example, holding on to a test tube and it got hotter, you would know that that reaction is exothermic, right? Because your hand's picking up all that energy, is why your hand's now on fire, because it's very, very hot. If you're holding the test tube and it gets really, really cold, you know that the reaction in that test tube is endothermic. It's sucking all the heat and energy out of your hand, which is why you feel cold. So the heat either being given off or absorbed is very common sort of example of a reaction has occurred. Obviously, here's some bubbling. That's the production of hydrogen gas, basically doing a little electrolysis of water, basically breaking apart water into uh, oxygen and hydrogen. I was gonna say that. I was trying to think. I feel like you guys did this one, but when you hooked that up, maybe you didn't. I don't remember. A color change, solid form, bubbles, heat or flame. Again, all examples of a chemical reaction occurring. This is like a titration type of reaction, and the formation of something blue in this case actually is a new compound that has been formed as a result of a chemical reaction. This is next Tuesday's event, making yellow all over the place. So you're gonna pour those guys together. You're gonna pour two solutions together, and you're gonna get a solid that's formed, a yellow solid that obviously wasn't there before. That's a precipitate, and that's definitely an example of a reaction that's taking place. More bubbles. That is also a reaction taking place when you light your Bunsen burner. That is a combustion reaction that takes place, and that produces a flame in this case. Obviously, a lot of heat comes off of it as well as it's burning as you do it. All right, so let's talk about chemical equations. The way that we represent chemical reactions is through a chemical equation. And we touched upon this when we hit chapter 9, since they assumed you did this chapter before you got there. But a reminder that a chemical equation basically has a couple of parts, and it does have an arrow in between. Stuff on the left there is our starting material. Stuff on the right-hand side of the arrow is what is formed. One of the most important things you should remember as we get into this chapter and we do things is you should always want to start with the correct formulas. And sometimes when we're going to talk about here balancing an equation in a second, people try to do those things together, write the formula and balance the equation at the same time, and you should never do that. So you should always want to start with the right things. Remember, some things like hydrogen gas, right, are diatomic, which means they need to be H2. If you put in just an H up there, you're going to be in trouble in terms of trying to balancing, and you're not going to get the right equation. So oxygen as well is O2, forms water. This is what is sometimes referred to as the unbalanced equation. And it's really important, if you do have everything in words, that you first start off with the correct formulas. Regardless of the balancing of the equation, you got to start off with the correct formulas for everything to work out correctly. This unbalanced equation can be read as molecular hydrogen reacts with molecular oxygen to yield water. Um, If you do see that, something like molecular hydrogen or molecular oxygen, that is basically hydrogen gas, oxygen gas. Again, H2O2 is what you want to use as the formula. Now, what's wrong with the above is, like I mentioned a second ago, it is what is referred to as the unbalanced equation. And what does that mean? If you add up everybody on the left-hand side of the arrow and everybody on the right-hand side of the arrow, you do not have the same amount of each element. So if you made like a little table here of like what is there, hydrogen and oxygen, and on the left-hand side and the right-hand side here, there are two hydrogens on the left. There are two hydrogens on the right. On the left-hand side, there are two oxygens. On the right-hand side, there are only one oxygen. So remember, if nothing is written, it's assumed to be one. So this is an unbalanced equation, and for the most part, you should never, ever use an unbalanced equation in anything. It should always be balanced. And the law of conservation of mass tells us the problem because in a chemical reaction, the only thing that happens is we break bonds and we make bonds. That is, as we talked about, I think, in a couple of places, only involves electrons. And that means that we never touch anything in the nucleus like protons. And that's important because protons are the one of the three particles that are the most important because the protons tell you what element it is, right? Everybody has its own atomic number. So because we don't do anything with the protons, if you started with 4 carbons on the left, you should actually end with 4 carbons on the right-hand side. They may be in different things, but you should not lose any elements along the way. So when we do a chemical reaction, we always have conservation of the elements. However many of those elements you start on the left, you should have the exact same number on the right. So we can fix this by balancing this equation. And the way that we balance the equation, as we'll talk about, is we only use coefficients. So we only use the numbers that come in front to balance this equation. So we could balance this equation very simply by fixing what is not balanced. And in this case, we could put a 2 here in front of the water. And when I put that 2 in front of the water, by the way, it goes for everybody that is behind it. So it counts for everybody behind it. So if I use my table up here on top, that would actually give me now 4 hydrogens, and it would give me 2 times 1 for the oxygens, 2 oxygens. And what usually happens is what we just see here. We just fixed the oxygen, but we kind of screwed up the hydrogen, and that's very common sort of procedure. We could very easily fix the hydrogen now by going to the left-hand side and also put in a coefficient in front. And we could put a 2 in front. And again, that 2 goes to everybody behind, which is just that. And that 2 times 2 gives me 4. We still only have 2 of those guys. And now we actually have a balanced equation. And the only thing that we changed are the coefficients. So when you balance the equation, that is the only thing that you can change are those numbers that come in front. Why can I not just change the number on the bottom? What happens if I take that 2 and change it to something else there in water? Is it still water? It's not water anymore, right? So water is H2O. So if you change the little bottom number, it's no longer what it's supposed to be, right? So you should never ever touch the bottom little numbers, the subscripts. You should only change the things that come in front. You also shouldn't do weird things that people like to do, like insert big numbers in between and stuff. So don't do that either. So only the things in front should change it. We never change the subscripts. Otherwise, we change actually what the thing is, and we don't want to do that, obviously, in this case. Any questions on that there? Yeah. Not affect this guy? Because technically speaking, even though there's not a number in front of oxygen, these are 2 separate things, the H2 and the O2. And technically speaking, the coefficient in front of oxygen is 1. And that's why technically this is 1 times 2. And that's how we get to the 2 oxygens there. They are not joined at this point, so they're basically 2 separate things. The reason the two on the right counts for both of them is because this is a compound and all those elements are together in that one compound, so it counts for everybody that's behind it. Yeah. Other questions? So again, as I mentioned, we can balance it by changing the coefficients and putting our 2's in there like we just did. And obviously that's going to give us our balanced chemical equation. And when we look at the chemical equation, as we talked about, I think in chapter 10, there's two main parts to a chemical equation. On the left-hand side of the arrow, those are what are known as our reactants. So over here, these guys are reactants. And they are the starting material in this chemical reaction. On the right-hand side, that is our products. And in this particular equation, there is only one product, but you could have multiple products on the right-hand side. You could have 2 or 3. Um, Usually about 2 on each side is a lot, but you can't have upwards of 3, in some cases maybe more. It always goes from reactants to products, and that is always how the equation is written. Actually, we'll come back to that, actually, I think. Now, let's talk about some other information that we very often see in chemical equations. We oftentimes will see the states of everybody. And when we're talking about that is what state is everybody in? Is it a solid? Is it a liquid? Is it a gas? So we oftentimes will see an S next to the formula, which obviously means it's a solid. We'll sometimes see an L next to the formula, which means it's a liquid. We will see a G next to the formula, which means it is a gas. I think we'll see it in a second, but I'll put it up here with the others. We do have AQ, which means it's aqueous. It's a basically water environment. And again, a reminder, and I think we might have touched upon it, but just in case we didn't, there is a difference between these two. Again, they are both in the liquid state, if you will. They're both basically liquids. But the difference between a liquid and something that is aqueous is a liquid is just a pure substance by itself. So there's nothing else with it. So an example of a pure liquid would be just water by itself, and that would be considered a pure liquid. Something that's aqueous, you take something like a pure liquid, like water, and you can mix it with something else like sodium chloride, which is a solid. This will actually dissolve in the water and it will make a sodium chloride solution that is aqueous. And aqueous is basically a homogeneous mixture. It's basically two things together, or more, two or more things together. And a aqueous guy is a solution or a homogeneous mixture. So a liquid is just one thing by itself, both liquid states. So here you can see we got some gases happening here. We got a mixture of solid gases and liquids in that one. In most cases, we do use a chemical equation to represent a chemical reaction that is taking place. We can also use a chemical equation to represent a physical process that's occurring, and that's what we see down here. This is liquid water going to solid. That is freezing, right? And that is a physical change, but we can use an equation to represent that. This is our liquid going to gas. That's evaporation. Also a physical change. A lot of times we do use equations to represent chemical changes, but we can also use equations to represent physical changes that are occurring as well. Any questions on that there? Couple of other things that you commonly maybe will see is sometimes things are written on top of the arrow. So for example, if we took some solid sodium chloride, what this would mean in this case is we're dissolving this in water. So sometimes they'll put up there on the arrow what you might be dissolving something in. I would say as well, very commonplace up on top of the arrow is a catalyst is usually listed. And again, a catalyst, as a reminder, is not a reactant. It's not a product. And it actually does not get used up in the reaction. It is there simply, as we talked about, I think in chapter 10, to speed up the chemical reaction by finding, if you remember, sort of a more efficient pathway for that reaction to occur. A lot of times catalysts are metals, so sometimes you'll see something like PT written up on top, like platinum. Sometimes catalyst can be something like an acid, which is sometimes abbreviated with an H plus. Just kind of puts things in the right environment and stuff like that. It's not considered, like I said, a reactant or product. It actually is still there when the reaction is over. It is there just again to usually facilitate the reaction occurring a lot faster and a lot more efficient, if you want to think about it in that sense. All right, I think was that everything there? Catalyst, that. I think so. All right. Then let's talk about balancing equations and some of the steps that you could follow. I will say that probably most people, when they go to balance an equation, will kind of take more of it's just a trial and error type of approach. But there are some really important things to sort of think about. First off, if you are given everything in words, as I mentioned earlier, it is really, really important to make sure, forget about the balancing thing. You should just think about what are the proper formulas. You should think about it in a sense like nomenclature, like I need to put these things together in the correct formulas first. And that is what you want to get down first. Then you should balance. So that should always be the order. Correct formulas, then balance. Don't try to do both of those things together. What most people do is they do try to do both of those things together and they end up with the wrong formula and they sit there frustrated because they'll never be able to balance it because you're not starting with the right formula. So that's really, really important. Where that happens a lot is, and you'll come across this perhaps, is you're given the reactants in an equation and you're asked to write the products and then balance the equation. And very, very commonly people, when they try to like predict what's on the right-hand side of the arrow, will do that. They'll kind of like balance and write the formula together and they end up with the incorrect formulas. And again, it never, never balances. So always correct formulas, then go back with coefficients to balance it. As we talked about, pretty much coefficients is the only way to balance it. You need to change those coefficients to do so. I am personally a big fan of like making a table like I kind of did on that previous one. Just have all the elements and a table kind of organizes things for you and you could kind of figure out where to go. It oftentimes will kind of point you in the right direction. I am also a pretty big fan of just to make it as simple as possible, which means whatever looks easiest to you to balance, start there. That seems like a really good idea rather than doing that. Some people will say try the most complicated thing first and balance that, and that's a good approach in certain cases. But I would try to do maybe what just looks easiest to you. And at some point, everything should fall into place. You will screw up things along the way as you're balancing, but eventually you'll hit the right coefficient combination that everything should kind of fall into place and everything will be right. The last thing that you should do is check to make sure that your equation is balanced. And there are two things that you have to make sure of when you are done balancing an equation if you want to balance it correctly. The first thing is they all need to be whole number coefficients. So in your balanced equation, if you balance the equation correctly, you should have only whole numbers. There should be no decimals, no fractions. Everything needs to be a whole number in terms of the coefficient. They also need to be the simplest set of whole numbers. So what do I mean by that? Somebody could look at an equation, for example, and go, okay, well, 2a plus 4b goes to 6c, for example. And we'll just say that this equation is balanced. And maybe you see the sort of larger numbers to balance it. And it is correctly balanced in the sense of there are the same numbers on each side. But with each of these coefficients, right, I can reduce all these coefficients down by 2, yeah? And I should do that to get the properly balanced equation of a plus 2b goes to 3c. That would be my properly balanced equation. So if you balance the equation and then look at the coefficients and go, I can reduce down all the coefficients. And the key here is you need to still be able to hit whole numbers on all of them. Yeah. So every single one still needs to be a whole number. You need to reduce it down to the simplest set of whole numbers by doing so to have a properly balanced equation. Any questions on that there? Here's another approach, just in case you don't like the one we just talked about, but we're going to go through some as well. All right, let's talk about how to do this here. Let's do one together so we can kind of see it. All right, so if we're going to balance this equation, I'm going to do it with you here and just kind of take you through how I would balance this equation. So for the sake of not trying to squeeze in all the numbers, I'm just going to rewrite it underneath here. So I got some space. All right, so the first thing that I would do is, like I said, I would actually make a table, and left-hand side is my reactant side, right-hand side is my product side, and what I would put in that table is all the elements there are. So there's nitrogen, there's oxygen, and there's hydrogen, basically, right? So now what we're going to do is just basically count up everybody and see where we're at. So when I go to the left-hand side, there is one nitrogen. When I go to the right-hand side, there are two nitrogens, yeah? When I go to the left-hand side, there is one oxygen. When I go to the right-hand side, there is one oxygen. A reminder that if you do not see a subscript, it means there's one of those things, right? So again, we typically in chemistry don't write one. So if you don't see anything, one is the answer. Here on the left-hand side for hydrogen, there are two. On the right-hand side for hydrogen, there are two. First off, any questions where I got those numbers from? Yeah. All right, so for me, what looks probably the easiest to balance, first off, oxygen is already balanced, so I'm not going to touch that to start with, right? Hydrogen is already balanced. And this is sort of the benefit of the table. It kind of directs me in nitrogen is really the only thing that's not balanced, right? So instead of just jumping in and start throwing numbers down, right? You got like a plan here. You can see hydrogen, oxygen's good. Nitrogen's not good, so I'm going to start there. So to start there, I need to make the one on the left-hand side a 2. So remember, only coefficients. So I'm going to put the coefficient here on the left. Again, that does go for everything connected to each other behind it. So that would give me now 2 nitrogens. It will give me 2 oxygens, and I still have 2 hydrogens at this point, right? At this point, like I mentioned before, most commonly happens, I just fixed nitrogen, but now I messed up oxygen, right? But I could still look at my table and see nitrogen's still good, hydrogen's still good, so oxygen seems like the next good place to go. So the table could kind of help guide you as to maybe where to go next. I need to fix the oxygen on the right-hand side. So again, I need to turn that 1 into a 2, so I'm going to put a 2 in front of it. Again, it's going to go to this one and the guy behind it as well. So that will give me 2 nitrogens right here. That will give me 2 times 1 back here for 2. And 2 times 2 for the hydrogen will give me 4. I have now fixed the nitrogen. I have now fixed the oxygen. And the last thing that's not balanced now is hydrogen, which I could clearly see. I just need to come back to the left here and put myself a 2, which again will count for everybody behind it. That's going to give me 2 nitrogens, 2 oxygens, and 2 times 2 is 4. I now have my balanced equation at this point, the same number of elements on each side. And again, a table can be very helpful to do that. It kind of organizes things for you. It also kind of directs you in maybe the right place to start or where to go next. Okay, let's take a look and see how you're doing. So again, I'm going to make a table. So I got my reactant side, I got my product side. Just going to list all the elements that are there. So we got carbon, we got hydrogen, and we got oxygen. And again, I'm just going to kind of make a table of what we got to start with. So on the left-hand side, I got 3 carbons right there. On the right-hand side, I got 1 carbon right there. Left-hand side, I got 8 hydrogens there. Right-hand side, I have 2 hydrogens there. Left-hand side, I got 2 oxygens there. Now on the right-hand side, how many oxygens do I have to start with? I have 2 here plus, don't forget the one over here, that is 3, yeah? So again, we got some oxygen and a couple of things, so you want to make sure you count it correctly. All right, so clearly in this case, we got nothing balanced, so that's not a great start. Again, I'm going to go with what I think is the easiest. And for me, I just think carbon looks pretty easy. So I'm going to start with carbon. I'm going to put a 3 over here. Again, that is going to count for everybody behind it. So that would give me 3 carbons. It will still give me 2 hydrogens. Now, in terms of oxygen, I do have 6 oxygens in the first one, and I still have that 1 oxygen over here. So that is a grand total of 7 in this case, right? So we want to make sure we don't forget about the one on the right there. First off, any questions on that there? We didn't do anything on the left-hand side, so that obviously stays there. Now, I fixed the carbon. I am still not so great on hydrogen and oxygen. Which one do you think I'm going to go for next? I am going to go for hydrogen. And the reason I'm going to go for hydrogen is it is the easiest. And what I mean by that is when I look at oxygen, I have oxygen in one place here, right? But when I go to the right-hand side, I have oxygen in 2 places there, yeah? Best to keep a situation like that for the end, yeah? And just take care of somebody that is like in one spot on each side, yeah? And that's a much easier approach than jumping at oxygen first here. So to fix the hydrogen, super simple here. We're just going to put a 4 in front of the hydrogen to get us to 8. That again is going to go to both of those guys. So we got 3 carbons. I have 8 hydrogens. Now in terms of oxygen, and this is why I didn't want to go for the oxygen first, perhaps, I got 6 here, and I have 4 times 1, which is 4. So my grand total now for oxygen is 10. And that works out pretty easily because to fix oxygen on the left-hand side, all now I have to do is put a 5 right about there. And now we will have 3 carbons, 8 oxygens or hydrogens, and 5 times 2 is 10. And now we have a balanced equation. So my recommendation is you get a situation like this, which you commonly do a lot with oxygen, maybe nitrogen as well, is if you see that thing is in multiple things on one side and like one on the other, I would probably save that one for the end and focus on the other ones, which are just kind of in one place on each side of the arrow, and that's a lot easier sort of move. Any questions on that there? All right. All right, so why don't you give this one a go? Why not? That's some words. Turn them into formulas and see what you get here, yeah. So what is diboron trioxide? That is some prefixes, right? So that's good. So that is like a B2, yeah. Tri is 3, oxygen is O. B2O3 reacts with water. What is that? I hope we know, right? That is H2O. To form means you have an arrow, right? And I forgot what we formed there. Was that boric acid? It was BOH3. Little BOH3. That is our unbalanced equation in this case. So go forward and balance it up. Yeah. So again, a reminder, as I just did there, I didn't care about the balancing part. I just made sure I have all the proper formulas down. Yes, sir. It is. It's all one compound. Yeah. Might have been a little bit bigger of a space than, but it's all together. Yeah. Okay, so let's take a look. Again, I'm going to make a table here, reactant side, product side. In this case, we got boron, oxygen, and hydrogen, it looks like. All right, so just counting what we got going on, we got 2 borons there on the left, We have just one on the right. We have three oxygens there. Once again, we do not want to forget about the oxygen there. So that is a grand total of four on the left. Now, in terms of the oxygen on the right, as was questioned, this three does get distributed to everybody in the parentheses only. So whatever's in the parentheses is where that goes. That would give us three for the oxygen. Hydrogen there, we would have two, and once again, that would give us three, distributing that to our hydrogen. So in this particular case, not a lot to work with. So again, I'm just going to keep it as easy as possible. To me, it looks like boron is the simplest thing to fix. So we could fix that by putting a 2 in front of it. Now this 2 does again go for everybody behind it. So it goes to here, it goes to here, and it goes to there. It goes for everybody that's there. So that's going to give us 2 borons. We do have to kind of multiply in and then multiply out, if you will. So that's basically 3 times 1, which is 3, and then 3 times 2, which is 6. Same thing for the hydrogen, 3 times 1, which is 3, and then 3 times 2 in the front there is 6. Because basically what that is saying, right, is at this point we have 2 of these, and that gives us our 2 borons. That is basically 3 oxygens there and 3, which is 6, 3 hydrogens and 3 hydrogens, which is 6, right? So that is how we get to all those numbers. At this point, clearly we want to touch anything on the right-hand side because that's going to be a headache if we start messing with that. So now we want to go to the left-hand side and fix it. And again, I ask you, which one should I go for first, oxygen or hydrogen? Hydrogen. Again, here we see oxygen in one place, 2 places, and here hydrogen's only in one place, really on each side. So hydrogen is much better choice here. Hydrogen, very easy to balance. We just need to get it to 6, so we're going to put a 3 in front. That's going to count for everybody behind it, and that's going to give me still 2 borons. Now, in terms of oxygen, we do have 3 right here. That 3 in front will also give me 3 right there. So 3 and 3 is 6. And 3 times 2 is 6 as well. By just fixing the hydrogen in this case, it actually fixed the oxygen as well. And that sometimes happens a lot. You can fix. So let's see how you're doing on this one. Again, we're going to make a table here. So we got nitrogen, hydrogen, and oxygen. So on the left-hand side, we got 1 nitrogen. Right-hand side, also 1. Left-hand side, 3 hydrogens. Right-hand side, 2 hydrogens. Left-hand side, 2 oxygens. Right-hand side, 1. And again, we got 1 there, which is 2. Actually, in this case, everything is balanced except for hydrogen. In this particular case, we actually need to put a number on both sides, right? And that's because we have 3 on one and 2 on the other. The common number between 3 and 2 is 6, right? You can just multiply them together and you get 6. So to make my hydrogen on the left a 6, I do need to put a 2 there. To make my hydrogen on the right a 6, I do need to put a 3 there. So let's see what that did. That's going to give me, as obviously this goes for everybody, 2 nitrogens. 3 times 2 is 6 hydrogens, and I still have the 2 oxygens. On the right-hand side, I have 1 nitrogen. I have 3 times 2, which is 6 hydrogens. I have 1 oxygen there, and 3 times 1 is 3 there. So that is a total of 4 oxygens at this point. Once again, at this point, I'm going to fix the nitrogen as it is in one spot on each side. And I could do that by simply putting a 2 here. And again, that's going to go for everybody behind it. So that will give me 2 nitrogens. We got 6 hydrogens. Now in terms of our oxygen, I have 2 in the first one. I still have the 3 in the second. And that is 5 at this point. Obviously here we do need to fix the oxygen. So clearly at this point we should just go to the next question. No, I'm just kidding. We shouldn't do that. Maybe just leave this one blank, guys. But we need to basically turn a 2 into a 5. We definitely don't want to play with any of the other coefficients because we kind of already put them in place. So that's just going backwards. So we do need to kind of turn it into what we need. And you could do something like perhaps a 5 over 2. And if you do a 5 over 2, which looks like a fraction to me, is we will then end up with 2 nitrogens, 6 hydrogens, and when you take 5 over 2 times 2, those cancel, and you actually end up with 5 oxygens. And it is balanced at this point. Is it correctly balanced, by the way? No, because now I just put a fraction, which I remember I said I shouldn't do that, right? So this brings up a really good example of you absolutely can use a fraction to balance the equation, and you sometimes do need to use a fraction to balance the equation, but you cannot leave it like that. So what we need to do at this point is, now that we have the equation balanced, we need to get rid of the fraction. And if you remember, to get rid of a fraction, you multiply by the denominator. I think that's the thing on the bottom. So I'm going to multiply the entire thing by 2. And if I do that, that's going to give me 4NH3. That will then give me 5O2 goes to 4NO plus 6H2O. And if I did not screw this up, there's 50-50 chance, we should still be balanced at this point. So let's see. We now have 4 nitrogens on the left. We also have 4 on the right, so that's good. We have 4 times 3 here, which is 12 for the hydrogens. We have 6 times 2, which is 12, so that's good. For the oxygens, 5 times 2 is 10. Over here, that is 4 oxygens, and over here, that is 6 oxygens, and that is 10. That is a balanced equation. So it does oftentimes happen when you have like a diatomic element molecule there, and that guy is in a couple of things. Oftentimes, a fraction is a really good way. How do you choose the proper fraction? Well, you should not overthink it. The top number, if you remember, is the number you need. So if you remember, before we did it, we needed a 5, right? So that's what goes up on top. The bottom number should match the subscript, which is the 2. So bottom number should match. Top number is the number you need. You'll always pick the right fraction if you do it that way. Any questions on that one? Yeah. Because we have it balanced here at this point with the fraction, but we cannot leave it as a fraction because to have a properly balanced equation, they all need to be whole numbers. So we basically have to clear the fraction, and the denominator here is a 2. So if we multiply it by 2, that will get rid of the fraction, and we have to multiply everybody by 2 to, yeah, you multiply by denominator to cleared fraction. Yep. Other questions? Yeah, so if we went back a step to like here, this column, we had 2, 6, and 5, and really the oxygen is what we're looking at. And if we come back here, actually here, I think it was, we had 2, 6, and 2. So everything was balanced except for the oxygen. And we basically needed to turn that 2 over here into a 5. So the top number is the number we need, which is the 5. So that's why we chose 5 for the top. It's basically the number we need to get there. The bottom number should always be, I kind of scribbled over it, but the subscript that's there. And in this case, the subscript was a 2, and then that will get you the right sort of fraction. If you follow that sort of formula, you should always pick the right fraction in that case. Question on that there. Now, a couple of things here to finish up on in terms of balancing, a couple of other things that you sometimes come across. Let's say you had something like this, right? And we look at this equation, and maybe again, this would be one that you just want to go to the next one, maybe because there's a lot of our favorite things. See, I went to the next one without trying to do that, I think. Where did it go? Oh, there we go. There it is. It has a lot of polyatomic ions in it, right? And if you want to go through and balance it sort of element by element, you could absolutely do that. The problem, though, is when you have something like this that has a lot of polyatomic ions in it, there's a lot of like multiplying in and multiplying out if you do it element by element. And what oftentimes will happen is people will make a mistake when they try to do that. So my recommendation is if you see you got some polyatomic ions sitting there, on both sides of the equation, and they look the same in a sense. Like that's NO3 and that's NO3. This is OH and that is OH. My recommendation would be to keep them together and actually just balance them as like whole units. And what I mean by that is if I were to do this, I would take perhaps the nitrate, if you will. And the nitrate over here, I have 2 on this side and I have 3 on this side. So the common number there is, again, 6, right? So we want to get each of those units to 6. So to get this nitrate on the left here to 6, I would need to put a 3 in front of it. To get the nitrate to the right to a 6, I would need to put a 2 in front of it. And what that would essentially give me is 6 nitrates and 6 nitrates, right? So everything is good in terms of that. Now, what you do when you do this sort of method is whatever you balance here in terms of nitrate, whatever that is attached to is like where you should go next. So obviously my magnesium now is a 3 on the left. My magnesium on the right here is a 1. I could put a 3 there, right? That's going to fix my magnesium, but that will then give me how many hydroxides? 3 times 2 is 6, right? So then I could come over here to my hydroxide and put a 2, and now I am completely balanced. And much easier to kind of keep those guys together, balance those polyatomic ions first, and everything will sort of fall into place as you go through it. So you hit the polyatomic ion, and whatever it's attached to, that's where you go next, and you just kind of follow that pattern. Let's see here. So why don't you try a couple of those? So why don't you finish up by balancing these guys here and see what you come up with. And again, you got some polyatomic ions on those first 2, so maybe keep them together. Okay, so since we're getting to the end here, let's kind of go over these here just to kind of finish up this chapter here, since this is actually it. Um, Again, when I would look at this, I definitely see a polyatomic ion on opposite sides of it. And you do need obviously the same polyatomic ion on each side, opposite sides there to do this method. And that's what I'm going to actually focus on here and just kind of balance it using the polyatomic ion. So what I want to think about here is in terms of sulfate, I have 3 of them. And over here, I really have just 1 sulfate. So that is where I'm going to start. So I have 3 on the left, 1 on the right. I'm going to put a 3 in front of here. What that's going to give me now is 3 sulfates. Now, this is what I was talking about a second ago. Because I fixed the sulfate, what is attached to the sulfate is actually the calcium here, right? And that 3 does change the calcium to 3. And that's actually where I should go next. So now I'm going to go back to the other side to calcium, and I very easily know I need a 3, right? Because that's what I did on the other side. And that 3 goes for the calcium, but it also now goes for the chloride, right? Or the Cl. And that would give me 6 CLs. And that is where I should go next. So because that was attached, that's where I'm going to go next. So I'm going to go back to the right-hand side, and I have 3 CLs over here. So to fix that, I'm going to put a 2. That will give me 6 CLs here. How many irons does that give me? That will now give me 2, which, like I said before, is actually pretty good because I actually need 2 irons on the other side. And now I'm balanced by just doing that. So you want to balance the polyatomic ion, whatever it's attached to, that is where you should go next on the other side. And then whatever that's attached to, you should go to that other side and kind of go back and forth until you get it balanced. Any questions on that one there? Now, if I look at the next one, I do have a couple of polyatomic ions. I got nitrate on both sides. I also have phosphate on both sides. You could actually start with either one. And one may work better than the other. So I'm going to do the one that doesn't work great just to show you it's not a big tragedy if you choose the wrong one. So I'm going to start with the nitrate. And over here I have 2 nitrates. I have 1 nitrate. So to fix that, I'm going to put a 2 in front of it. That will give me 2 nitrates. That will also give me 2 coppers. Why do I know that's a bad move? Because on the other side, how many coppers do I have? have 3. So that's not going to work. So that one doesn't work really well. So no big deal. That's why they invented erasers, right? So you just get rid of that and give it a go again. So clearly here I did the nitrate first, so I'm not going to do that again. I'm now going to go to the phosphate here. I got 1 phosphate here. I got 2 phosphates here. I'm going to put a 2 over here to balance out my phosphates. And because I balance my phosphates, that will then give me 2 times 3, which is 6, I'm going to say carbons, but coppers there. That is where I should go next. So now over here to the right, I need 6 coppers. That then will give me how many nitrates? 6 in this case. That is where I'm going to go next. I already have 2 nitrates. So to fix that, I'm going to put a 3. That will give me 6 nitrates, gives me 3 bariums, and that is exactly the number that I need over here to balance it. So again, by keeping those polyatomic ions together, it oftentimes will make it a lot easier to balance. You can still go element by element if you prefer, but it is a lot of like multiplying and keeping track of things, and it can get a little bit more confusing. Any questions on that there? Let's take a look at the last one just so we don't have it hanging out loose here. So C4H10 plus O2, a little CO2 and water, I think it was. So this does not have polyatomic ions, so I'm going to go back to the table method, and that's probably the best approach. We're going to go reactants, we're going to go products, carbon, hydrogen, oxygen. We got 4 carbons there, 1 carbon there, 10 hydrogens there, 2 hydrogens there, 2 oxygens there, 2 and 1 is 3. So just like we kind of did on the previous one, I'm going to go with what's easy. So carbon is easy here. So I'm going to fix carbon by putting a 4. That 4 once again goes to everybody behind it. 4 carbons, 2 hydrogens. That is 8 oxygens in the first one, plus the 1 over here. That is now a total of 9 oxygens. Once again, like we talked about a number of times, I am not going to play with the oxygens at this point because it's in multiple places. I'm going to go to hydrogen next. Hydrogen can be easily fixed by putting a 5 here. That 5 is going to go to everybody over here. So I got 4 carbons. 5 times 2 is 10. Oxygens, I still have 8 here. I have 5 times 1 over here, which is 5. 8 and 5 is 13 at this point, yeah? What should I perhaps do at this point? I need to turn a 2 into a 13. What's a good way to do that? I'm going to say like a fraction, yeah? So how do we choose our fraction? What number do we need? We need 13. That is what goes up on top, yeah? This number here goes on the bottom, yeah? So 13 over 2 will be a winner. And that will now give us 4 carbons, gives us 10 hydrogens. And once again, if you take 13 over 2 times 2, they cancel and leaves you 13. I again cannot leave it like this, right? So to clear the fraction in this case, I need to multiply the entire thing by 2. And that will give me 2C4H10 plus 13O2, 8 CO2 plus 10 H2O. And once again, if I didn't screw up, which I hope I didn't, it is still balanced. 8 carbons on each side, 20 hydrogens on each side, 26 oxygens on each side. 16 oxygens there and 10 there is 26. We are still balanced. Yes, sir. It's not the problem with it is there's a lot of parentheses lots of times. There's a lot of multiplying in, multiplying out. It will definitely work. It's